Hello everyone. So previously we had discussed on the topic Miller-Rabin primality test algorithm. Yeah. So today we'll be discussing on the topic Pollard's RHO factorization algorithm. Yeah. So now let's see what the definition states here. Pollard's RHO is a probabilistic algorithm. So similar to the this one Miller-Rabin, this one what do we call uh, primality test algorithm. So that's also the probabilistic algorithm. Yeah. So Pollard's RHO is also a probabilistic algorithm used to find a non-trivial non-trivial factor of a composite number efficiently. Non-trivial factor of a composite number efficiently. It works using a pseudo-random function and Floyd cycle. It works using pseudo-random function and Floyd cycle detection. Yeah, to identify repeating values that reveal factors. Yep. Next, let's get into the explanation part here. So now let's see what the so whatever we discussed here, the same thing will be implementing in the form of code. Yeah. So the algorithm relies on the idea that for a composite number n, if two numbers x and y becomes congruent, we generate a sequence using function like this one, f of x equals x square plus c modulo n. So this is the main thing. The only thing that we have to concentrate here. F of x equals x square plus c modulo n. Again, let me read this one out loud. Listen to this carefully. The algorithm relies on the idea that for a composite number n, if two numbers x and y becomes congruent, then we generate a sequence using the function like f of x function of x equals x square plus c modulo n. And basically we track the two sequences, right? One moves one step at a time, right? X, just keep this in mind. And the other moves two steps, nothing but y equals f of y, right? If they meet, we compute GCD of x minus y. This has to be positive, comma n. This often reveals the factor of n. This often reveals the factor of n. Yeah, the exact same thing. Let's implement in the form of code or articulate in the form of code now, right? So let's start writing the algorithm. First, we need random. So I'll just go with the import random. Yep. So this is fine. The next part is let me go with import math actually. Just go with math. So this is fine. Next, let's write the function to compute the GCD, nothing but greatest common divisor. So I'll just go with GCD here. GCD. So this is fine. A comma B. Yep. So within the helper method GCD, first the base case is if B is 0, then GCD is A, right? So Euclidean algorithm. So this one will be if B equals 0, then let's return A directly. Yep. So I'll just go with return 0. We know this. Yep. Next, let's recursively compute the GCD. All I have to do here is let's return here. Sorry, yeah, what we need to return here? GCD of B, comma A modulo B. So this is fine. After this, what we have to do? Basically, after computing the GCD, what we have to do? Let's go with a Pollard RHO function, right? So I'll just go with Pollard here. Just go with Pollard actually. RHO. So let me pass n here. Let me consider n as parameter. Now, if n is even, then we have to return 2 directly as a factor. We know this. I can just write it in this way. N modulo 2 equals 0. Then let me return what we have to return here. We have to return 2. Yep. So this is fine. The next step would be we have to choose the random constant c, right? C has to be greater than 1 and less than n. Yeah. So c, I'll just go with here random dot random. Let me go with the random and a random int actually. So let me consider this one from 0 to n minus 1. Any. We are just going with a random here, right? So this is fine, man. Yep. Next, let's do one thing. Let's initialize the starting values of x and y, right? X, let me initialize this one too. Again, the same thing, random dot random int. So here I'll just go from 0 to n minus 1. So this one we are considering from 0 to n minus 1. For this one, we have to consider from 1 to n minus 1. Sorry. Yeah, I got confused here. So for y, let me assign this one to x directly. Yep. So we are done with this part. Let's initialize the divisor as 1, meaning, so let me assign d to 1. So this is also fine. We have to loop until we find a non-trivial factor. So I'll just go with while d equals 1. Then what we need to do here, we have to move x one step, meaning I can just write it in this way. See, x equals x into x plus c. X equals x into x plus c modulo modulo n. Yep, so this is fine. Next, let's move y two steps, nothing but Floyd's cycle detection, right? So I'll just go with y equals y into, so this one, y plus c. Yep, so this is also fine. Modulo n. So this is modulo, not 5 actually. Yep, so next final one, x equals x into x plus c modulo n. This is fine. Y equals y into y plus c modulo, and this is also fine. Again, let's go with a y here. So this one, y into y plus c, same thing, modulo n. Yep, so this is also fine. Yeah, now we have to compute the GCD of x minus y, and then accordingly with the explanation part. We had discussed the same thing in the explanation part, right? So D equals, so let me go with GCD of absolute, I'll just go with the absolute. So this one, because we need this one positive number, also the absolute number, right? I'll just go with comma n here. So this is fine. Next step, if d is greater than 1 and less than n, we have found a non-trivial factor, right? So suppose if d is equivalent to n, then we have to retry with a different constant c. So I'll just go with return this one. Let me call the function Pollard RH over here, and let me pass the n, right? So finally, what we need to do, we have to return d. We have to return d actually. Yep. So this is fine. Yeah, now let's do one thing. We are done with the algorithm part. We know this. We are done with the algorithm part. So whatever we discussed in the explanation, the same thing we have articulated in the form of code or implemented in the form of code. Now let's go with this one example usage. Very simple one. I'll just go with n equals 8051. Yep, let me go with n equals 8051. So this is the composite number. Nothing but 8051 can be split into 97 into 83. Yeah, so I'll just go with here factor equals Pollard. So let me call the function here Pollard RHO. This one, let me pass the n. This is fine. Let's make use of the print statement just for the this one interactive purpose. So this one, I'll just go with a non-trivial factor of non-trivial factor of. So I'll just go with n comma. So I'll just go with is here. Yep. So this is also fine. Let me pass the factor here, right? So this is fine. Yep. So let me format this once so that this looks good. This is fine now. Yep. So we have this one. What do you call? Now we have the idea actually. Let me explain the algorithm once more so that we don't forget this one. See, so first we are importing random and math here, right? Random for generating the random numbers and math for the mathematical functions. Yeah. Though only GCD logic is custom here, right? So even though we are just importing math here, right? So this is fine. Next, what we are doing, we are just going with the GCD of a comma b, this one function. This is classic Euclidean algorithm for the GCD calculation or the computation. We know this one, yeah. So here it's we have this one 90 Euclidean algorithm we have discussed, right? This is fine. Next, we are going with the Pollard RHO. Listen to this carefully. If n is even, suppose this one line number 29 and 30. So if n is even, we are just returning 2. Yeah. Next step, what we are doing here, line number 32, we are picking a random constant c and initial values for x and y respectively. Yeah, that's what we are doing from 32 to 35. Very simple one. Then we are iterating using the function. The main thing, as I've said, this one f of x equals x square plus c modulo n. Then the same thing we are doing here, right? So while d equals 1, we are iterating using the function f of x equals x square plus c modulo n. Then we are making use of the Floyd cycle detection. X moves one step and y moves two steps. See here, x moves only one step and y moves two step here, right? Meaning we are making use of the Floyd cycle detection. Floyd cycle detection, we had discussed that one, Floyd cycle detection algorithm and the linked list based algorithms, right? You have to know the Floyd cycle detection algorithm. Yep. So this is fine. Basically, this is fine. X moves one step and y moves two, right? So finally, we are computing d equals GCD of this one x minus y comma n if only d is greater than 1 and less than n. So that's the factor actually. Yep, that's the factor. Yeah. If D is equivalent to N, then what we are doing, we are just retrying with a new C. We are just retrying with a new C. Yep. So this is nothing but the example usage. So what is the output that we need to get here? So non-trivial factor of 8051 is, as I have said, so this one will lead to, sorry, where is it? 8051. So this one will lead to 97 into 83, right? So non-trivial factor should be quite obviously 97. So again, algorithm, what it does, whatever the algorithm that we have written, internally finds the repeating pattern in the modular sequence. We know this one. Yeah. When the values of x and y, when the values of x and y that we have considered collide, it exposes a relation that is nothing but x equals y mod p, right? For some prime p dividing n. For some prime p dividing n, right? So we are making use of GCD of x minus y, this part. GCD of x minus y, where did it go, man? This one, absolute of x minus y, whatever we are making use of. Actually, we are using GCD of x minus y comma n that reveals that prime factor. This one, that prime factor. Yeah. So the answer has to be 97 here. Answer has to be 97, right? So let's check the same here as discussed. So yeah, let me give Control J here. Python followed by file name.py. A non-trivial factor of 8051 is 0. Somewhere we have done something wrong. I have messed up somewhere. Let's see. So mostly computing the GCD itself, I have done something wrong itself. It is not getting calculated here. We are getting 0, right? So if b equals 0, yeah, see here, if b equals 0, I have given return 0. If b equals 0, classic Euclidean algorithm actually, we have to return a in that case, right? So yeah, now this has to give us the correct output. Actually, let's check the same. Yeah, see here, a non-trivial factor of 8051 is nothing but 97. Yeah, so this is it. So basically, we are not making use of math here. We don't need this one, I believe. Let me check once. We are just going with a this one, right? What do we call it? Custom GCD function. Yeah, we are not making use of math anywhere. Let's check the same here. Yeah, we don't require actually math. Random is fine. Random is enough actually. Yep. So this is fine, man. Yeah, so we are done with the Pollard, this one, Pollard's RHO factorization algorithm. Yeah, so now as we are done with this particular algo, let me summarize whatever we have learned so far before moving on with the next algorithm. Yep. So let's discuss some 3 to 4 points actually, which is very important. Yeah, you have to know this one at any cost. Yep. So yep. Let's continue with the same. Let me summarize, right? So Pollard's RHO is fast for numbers up to 10 to the power of 18. Numbers up to 10 to the power of 18. So this is very important. Yeah. 10 to the power of 18. And efficient for random composite integers. And it is efficient for random composite integers, right? So this is fine. Let's move on with the second one. Actually, it uses modular arithmetic. It uses modular arithmetic. I'll just write here modular arithmetic, and along with it GCD, along with it GCD, modular arithmetic plus GCD plus cycle detection, right? So plus cycle detection, right? So this is fine. Yeah, so we went with modular arithmetic plus GCD plus cycle detection, right? To find the factors. It uses modular arithmetic plus GCD plus cycle detection to find the factors, right? So the third one here would be it's probabilistic. So we have discussed this one. It's completely probabilistic, right? Similar to the Miller-Urban, this one, primality test algorithm. It's probabilistic, meaning the results can vary between runs. Yeah, so this is fine. The fourth one is here. It's ideal for the CP, nothing but the competitive coding. So we make use of this one in the cryptography as well, right? So we make use of this one in the cryptography as well. Use cases and mainly in cryptography and the competitive coding. Yeah, competitive programming when dealing with a large semi primes. When dealing with a large semi primes. Yeah, so this is fine. So these are some of the points that we need to keep in mind. So these things you have to know at any cost, right? So this is fine, I believe. So we are done with this particular algorithm. Yeah, so we are left with only 2 algorithms within the number theory, this one based algorithms actually. So we are left with fast Fourier transform and number theoretic transform. Let's finish this tomorrow. Yeah, tomorrow will be let's go with a fast Fourier transform algorithm first. Yep. So for now, this is it. Thanks for watching, guys.